Hi everyone, welcome to Advent of Code Day 23. This video I'll be going over my solution in Python and sort of explaining how I approach the problem. Alright, let's get right into it. So in this problem, we have a input that's made up of hiking trails, which are these dots, through a forest, which are the pound signs. And you can see how the hiking trails sort of snake around. We're starting in this top left corner, finishing in this bottom right corner, or this little cutout. And there are these icy hills, represented by less than, greater than, lowercase v, and caret. And so these arrows, the direction they're pointing on, it's like a one-way tile, basically. So if I'm walking along here, hit this tile and go down, I can no longer go up. Similarly, if I go right here, I can no longer go left past up this icy hill. What the problem is asking us is, can we find the longest walk from the start to the end such that we obey the rules of the hills and that we visit each tile? No, we can only visit each tile once. So obviously, if we can visit each tile more than once, then we just have an infinite number of steps. We can keep stepping back and forth forever. But yeah, let's go into Python to sort of show how I approach this problem. So looking over here, down into our part1 function, first thing I do is find the start and end characters by looking at the first line and the final line of our input. Then I find what I call the junctions. And I call a junction wherever we have a point that's either open space or I guess an icy hill also, so just not the forest, such that there are at least there are more than two neighbors open. So for example, this space, both of its neighbors are open on left and right, but above and below is forest. So that would have exactly two open neighbors. Here, however, we have three neighbors, so I consider that a junction because we can go in different directions. Similarly, here's a junction, here's a junction. Actually wrote up a little visualization script so we can look at that. And here, this is all the junctions. I add an extra junction for the start and end. Yeah, we can see junction here, here. I just have it also printing out the locations of them, but yeah, we can see them just like I described. Any square with three or more neighbors. Then I go through this. I navigate the forest, trying to find the path from each junction to another junction. And what that sort of looks like is I essentially just use breadth first search, starting at each one of these junction points and continuing along until we run out of options and have hit all the other junction points. So for example, when we start here, we go along, hit this junction point, save that distance, and then since there's nowhere, since we've hit that junction point and there's nowhere else to go on the search, that search is over. From here, we can go down or right. If we go right, we sort of loop around, get up to this junction. If we go down, snake around, get to this, eventually we get to this junction. And so what that does is it builds out this graph here. And essentially our walk through the forest can be described entirely using this graph. So we start at the start at 1, 0, go down to this junction, have some options, but eventually we're going to get to the end. And what we want to do is find the maximum distance through this directed graph. And stepping back to our code, the way we can do that is using Dijkstra's algorithm, which finds shortest paths. The key difference we can make is by traversing this graph using the negative distances. So by minimizing the negative distance, we are maximizing the distance. So I just used a heap, Dijkstra's algorithm, propagating this negative distance dictionary, which contains the lowest distance to get to each point using the negative distance. Then finally at the end, I can just return the negative distance to the end, taking the opposite of that. And we can see we get 94 for the example. That would be, well, we can look at this, if that makes sense. 15, this is the same either way, but what's the most distance we can go through here? I think it's going to be 24, then 18. So we've got 15, 22, so this is 40, 64, 79, 89, 94. And so that is indeed our longest path. We can then apply that to the full input. We get a bit of a bigger graph, but you can see here it is more complicated, but the logic is exactly the same. We can just traverse this full graph and get the answer to the full input. Now, going back to the problem description for part 2, we have basically we're relaxing the problem such that these icy hills, we can now treat them as normal squares. We can go either way. And essentially what that does is it turns our directed graph into undirected, because now whenever we go to a node, we can also go back because there isn't like an icy hill preventing that. And now it's still asking us to find the longest hike. And so we're essentially trying to find the longest path on this, thinking of it as an undirected graph, and such that we can only visit each node at most once. So once or no visit. And this is what's known as the longest path problem. That's known to be NP-hard, which means that there's no polynomial time algorithm like Dijkstra's to solve it. And so we must use essentially brute force. So let's go back to the code. You can see for part 2, get the start and end just the same, find the junctions, store the negative values, this is all the same. Here is where it's different. This is finding the longest path using brute force, in this case, depth first search with backtracking. So essentially, I create, like a normal depth first search, I create this to visit list. But we're tracking a bit more information for each node that we add to this list. Instead of just the position, we're adding a full tuple of 4 elements. The first element is the node. The second element is our current distance, so the distance to this node. The third element is our list of visited nodes. And then the fourth element is the node that we want to traverse to next. And so we can see that during this loop, we're maintaining this max n_dist variable, updating that to the maximum distance to get to this final node as we traverse it in different ways. Then it's pretty simple what we're actually doing. We just append to this list using just like what's right in here. For each of, so say we're at this node, for each of the nodes that it connects to, because remember this is an undirected graph. So this one, and this one, we check if we've already visited it on this branch of the search. If so, we continue. If we have not visited it, we add another element to visit. So this will be another branch in our search, and update these values accordingly. So we have a new point. We need to increase the distance, mark this point as visited, and then set this next to try point. So yeah, that does it for this problem. Thanks for watching. As always, if you have any questions or comments, please leave them in the comment section below, and see you tomorrow for day 24.